Understand? Then plug in the next one. Minus this time. 1 over, so you're plugging in 2 here, right? So 2 times 3 squared. And then x minus 3 squared. Plus this time, 1 over 3 times 3 to the 3, x minus 3 cubed, plus so on and so forth. Make sense? Of course, these are just numbers, right? That's like 1/18. This is 1 over 81. All right, that's it. Done with that. Happy?
No.
Okay.
Define happy.
The way you feel right now. So look, in the homework that I'll give you what the homework assignment is at the end. You know, there's going to be different functions that you have to do, and the patterns, sometimes they're easy to pick up, sometimes they're a little harder. So make sure you go through those homework problems, and when you get into trouble, you know, you can look at the video and see how I pick up the patterns if you're having trouble with them. All right, so I'm going to bring up Wolfram alpha real quick, because I'd like to do an integration problem right now. So I'd like to do this. I'd like to integrate sine of x cubed. So let me bring up Wolfram alpha, see if it's willing to help. Server not found. Oh, I should probably turn on my Wi-Fi. All right, so I'm going to ask Wolfram alpha here to integrate sine x cubed. That's all I'm going to have. That's all I'm going to type in.
You've been doing it wrong the whole time? Yes.
What the hell?
There it is. Whoa. Of course. It's negative 1/2 I x gamma. Is that gamma? No. Yeah, it's the incomplete. It's the incomplete gamma function.
Oh.
Of this, it's got imaginary numbers in there. That's a mess,
You know what?
right?
When you typed that in, I thought exactly what that was.
You were thinking that, right?
Yeah.
Okay, so wow, it's just a mess. Now, if we scroll down far enough, I'm sure we're going to see.
E 2/3 I x cubed.
Let's see.
Just a little middle finger.
We have some power series
Somewhere.
here.
So
Okay.
we have to get to that. That's your test.
All right, so let's see if we can integrate this, all right? Let's see if we can. Well, Wolfram tried, and it gave us an answer. And while I've,
It could not be found. It's dying.
There we go.
You broke Wolfram alpha. Broke the internet, Professor.
Yeah, I don't have. Do you remember how I was talking to you about the approximations? This just to remind you what I meant by that. These approximations start to converge to the true function. So the red function is the function we're trying to come up with the Taylor series for. And then we start creating the series. See it right here? We just had one very similar to this. We had log 3 out front, right? So you can see how these dotted graphs start to converge to the red one. And I thought I had this code where I could slide this back and forth, but I don't. That's how changing the A would change how it looks. What would happen is if I changed A, then these dotted graphs would maybe be closer to this, and they would converge faster because you're closer to it. All right, let's not worry about that. All right, so let's get to this integral. Yeah, no, there's nothing you can do to this, all right? There's no method we have. But we do know this. We do know the Maclaurin series for sine, right? The Maclaurin series for sine we did last class. We know that sine x is equal to the sum n equals 0 to infinity of -1 to the n plus 1. Double check me on this. X to the 2n plus 1 over 2n plus 1 factorial. Or is it to the n? It should start out positive, I think, so I think that's wrong. That is,
Negative 1 to the n.
it's just to the n, yeah. It should start out positive. Remember, these formulas are on page 484, all right? These, I'm thinking I will provide these for you on the final.
Yeah.
Okay. All right, so we know that we can expand sine x like that, right?
Yeah.
What we have here, though, is sine x cubed. So instead of putting x there, replace your x with x cubed. And that puts that as x cubed, but then to the 2n plus 1, right? So if I do the algebra on this, this is just sum n equals 0 to infinity, -1 to the n, but then I have x to the what? 6n plus 3 over 2n plus 1 factorial. Let's write out the first few of these, okay? Let's just to see what this looks like. Let's plug in 0. Plug in 0, you get 1, what is it? X cubed?
X to 9.
Plugging in 0,
Wait, X to.
right? X cubed, everyone okay with that? Yes? Okay, now plug in 1. You're going to get a negative, right? Negative x to the 9th over 3 factorial. Yes?
Yes.
Yes? Okay.
You got it.
Negative x to the 9th over 3 factorial. I'm going to write it this way. 1 over 3 factorial x to the 9th with a negative out front. That's the same thing? The next one should be a plus. I should have 1 over, what's the factorial going to be here? If I'm plugging in 2 for n, 5 factorial? X to the 15th. What's happening is these powers keep going up by 6, don't they? You can see it right here, 6n, so they keep going up by 6, and they started at 3. So I should have minus 1 over, now the denominator, the factorials are going up by 2, but they're odd numbers, right? That's from this. So 7 factorial, right? X to the 21 plus dot, dot, dot. All right, so what I've done here is we've said, look, we cannot integrate that with any technique we have. So what we're going to do is we're going to find the Maclaurin series for sine. Here's the Maclaurin series for sine, right? That or this written out. And when you integrate, you can integrate term by term, right? When you integrate, when you have addition or subtraction between things, we can do it term by term. So if I integrate this and then this and then this and then this, that should be the answer, right?
Yeah, but we have to do that to the nth term, though.
Well, we can't, right?
Well, that's my point. Is
But can't we integrate a power series?
yes.
We can integrate a power series. We learned how to do that 2 classes ago. So what I'm going to do now is I'm going to rewrite the whole problem, all right? I just wanted you to see this and look at it because I'm going to come back to this in a minute. Y'all got that down? Okay. So according to what we've learned about these Maclaurin and Taylor series, this integral should turn into the integral of this power series, sum n equals 0 to infinity, -1 to the n, times x to the 6n plus 3 over 2n plus 1 factorial dx. Now, when we integrate power series, we do not have to change the index, right? When we integrate a power series, we do not change that. It stays at n equals 0. All we do is do the power rule, right? The power rule, you just add 1 to the power, but you have to divide through by that.
Right.
Normally, it's 1 over n plus 1, and then x to the n plus 1. Yes? That's what it normally is? But here, our power is not n. I will also point out everything I'm circling here in red. That's c sub n. That's your constant. And this piece right here is like your x minus a to the n. Do y'all see it? Okay. So normally we would leave the c sub n alone, right? And do 1 over n plus 1, and then this to the n plus 1, right? Can't do it because it's 6n plus 3. But we can still add 1 to that power, can't we? We add 1 to this power, what do we get? 6n plus 4, right? And then we have to scale out by the same amount in front. So this should equal some constant of integration plus, no more integral, new series, and equals 0 to infinity, negative 1 to the n over,
6n plus 9.
pardon?
Would it be 6n plus 9 because the n is in parentheses?
What n is parentheses?
6n.
This is not, oh, no, you're not, okay. I see what you're doing. We're not adding 1 to n, okay? What we're doing is adding 1 to the power, right? So like if I said everyone in here, let's integrate x to the 18th power, you would just say 1/19 x to the 19, right?
Right.
Whatever this is, you're just adding 1 to it.
So if that was
So-
actually
So if it's 6n plus 3, you're going to add 1 to it, right? So it's going to become 6n plus 4. So this should be 1 over 6n plus 4 x to the 6n plus 4. Y'all see how that worked? This right here is just the antiderivative of this right here. Scale out by the power so that when you do take the derivative, this is going to come out and cancel, right? This is all just some constant. So that's it. This should be the antiderivative. Let's write out the first few terms of this. Okay? Can we write out the first few? I know it looks bad, but let's actually just write out. I have some constant plus, let's plug in 0. You get 1, 1, 1/4 x to the 4th. Okay, so I just have 1/4 x to the 4th. The next one should be negative, shouldn't it? So I'm plugging in 1 now. So I get negative 1 in here, 3 factorial. So I have 1 over 3 factorial times this with 1 in here is a 10. So times 10, and then x to the 10th, right? Plus 1 over, now we're plugging in 2, right? 2 in here, we get 5 factorial times, plugging 2 in here, 16, x to the 16th plus dot, dot, dot. Is that good enough? I claim that this infinite series is the antiderivative of sine x cubed. And the way to prove it to you is to take its derivative, right? Take the derivative of this, and you need to get sine x cubed. So take the derivative right now. Let's just check it. Derivative of constant is 0. What's the derivative of this? X cubed. Look on your page. Didn't we write out what sine x cubed is? Yep. Didn't we write? Wasn't that the first term, x cubed? Okay. Then take derivative of this. So minus, this is a constant. Bring the 10 out. 10's cancel. I just have 1 over 3 factorial, right? X to the 9th. Was that our second term?
Yeah.
Yes. And then you can keep going through this, and you'll see the 16's cancel. You have 1 over 5 factorial x to the 15th. And that matches exactly what sine x cubed is, right?
That's really cool.
This is really cool because this allows you to integrate things without actually having to integrate them. Yes.
So why did Wolfram alpha have like some weird equation?
Well, Wolfram is trying to give you a closed form of the antiderivative. It's trying to not give you an infinite series. So what we do is we have these functions, special functions that you haven't seen yet, that you wouldn't see till later, that actually say, hey, look, like when you have certain situations that, when you're trying to integrate, there's this special function that is defined. How do I explain this? They're like error functions. They give you the answer within some error, which is basically what the series is doing. We just have names for them. And so Wolfram Alpha, it's doing its best to try and give you something. And also, Wolfram Alpha is a little smarter than us. It works in the complex field also. So it's actually allowed, Wolfram Alpha is allowed to work in the real, in the complex numbers. Now I wonder what would happen if I type in here over reals. That means I can only, Wolfram Alpha is only allowed to treat x as a real number. That still gives me imaginary. Okay, well, no, hold on. It didn't this time, you see that?
What do you mean? So you can type in only real?
No, wait a minute, hold on. It decided to plot that instead.
That's what it is.
It decided to plot it.
Close enough for God.
Here, expand this graph.
Okay. You see this? Integrate this over reals. It didn't like that at all.
You're like, no, it has to be
It didn't like that.
imaginary, dude. Crazy.
All right. Okay, so theoretically now, if you were asked to find, let's plot it. Let's plot that function real quick. That looks like it. Plot. There we go. There's the plot of sine x cubed, right? That's the plot of sine x cubed right there. Got it? Okay. What I'd like to do is I'd like to rotate that around the x-axis on the interval 0, 1. I'd like to rotate around the x-axis, and I'd like to know the volume. Okay?
This is like the Gabriel.
Understand what I'm saying here? Yes? Okay, so how would I do that? If I take y equals sine x cubed on the interval 0, 1, and I rotate that around the x-axis, right?
Yeah.
Then my formula, if the graph looked like this, kind of look like that, right? The formula should be, the volume of that should be pi integral 0 to 1 of?
F of x minus g of x squared, both of those.
That's right, good. F of x squared minus g of x squared. F of x is the outer radius, g of x is the inner radius. The inner radius here is 0. So this is just going to be that function squared, right? And you sit there and you go, what the heck, how do I do that, right? Well, I can use a power reducing formula here, can't I? Mm-hmm. I could do pi, half would come out, integral 0 to 1 of 1 minus cosine of 2x cubed, right?
Bless you.
Bless you. Dx, right?
Now you at least know what.
And now you say, okay, I don't know. I don't know what this is. I can split this into two integrals, can't I? This first one will be no problem. The second one, you're going to now use the Maclaurin series for cosine.
Negative.
Right?
With cosine.
Yeah, the minus I'll just put in front. Do you all understand? You could do Maclaurin series for this. We just did the Maclaurin series for sine x cubed. You could do the same exact process for cosine x cubed. Or 2. The 2 would be in there also. So your form, let me see. Let's just write down, what would the Maclaurin series for this be written in some notation? Forget the negative, okay? It would be n equals 0 to infinity, negative 1 to the n, and then
1 over 2n parentheses factorial.
1 over 2n factorial, and then this is x to the 2n, right? But it's not x for us, it's 2x cubed to the 2n. Understand? That's what the power series for this would be. And then we could put the 3 and the 2 together, right? This becomes 6n. And we could pull the 2 out. Then you could integrate the power series. Once you integrate the power series, you have the answer, right? And then you just plug in your two endpoints, 0 and 1. What I'm getting at here is that this opens up just an infinite number of possibilities of what we can integrate, right? As long as we can convert it over to its power series. And this is what makes